Hi everyone. In this video, we are going to discuss about the necessary conditions for both roots of a quadratic equation to be between two real numbers. Let's suppose we have a quadratic equation which is ax squared plus bx plus c equals 0. If the two roots of this equation are alpha and beta, assuming alpha is less than beta, then we are going to find out what would be the necessary condition for alpha and beta to lie between two real numbers like k sub 1 and k sub 2. If the quadratic equation is ax squared plus bx plus c equals 0, then we can assume that our quadratic function would be f of x equals ax squared plus bx plus c. And then for this function, I have drawn the possible graphs here. When a, the leading coefficient, is positive, I have the graphs here, and also I have two other graphs down below when the leading coefficient a is negative. So now first we have to understand that we are talking about two real roots, right? And k sub 1 and k sub 2 will definitely be outside of the parabola. So let's first try to plot the k sub 1 and k sub 2 on the positive x-axis. In the first diagram, I am using the two red dots here to denote the location of k sub 1 and k sub 2. And if k sub 1 and k sub 2 are located like this, then only the two roots of this quadratic equation will be between them. That means k sub 1 and k sub 2 have to be outside of the parabola. They cannot be inside the parabola, right? So let's try to understand the first necessary condition, which is that the equation must have two real roots. That is our required condition number 1, right? Now, when can a function have two real roots? Well, if the discriminant is greater than or equal to 0. If the discriminant is negative, then a quadratic equation cannot have real roots. It can have real roots only when the discriminant is non-negative. So let's make a note of that. So the first necessary condition is that the discriminant must be greater than or equal to 0. And now let's talk about the second necessary condition. Now, if k sub 1 has to be outside of the parabola and has to be on the left hand side of the parabola, and k sub 2 has to be on the right hand side of the parabola, assuming that k sub 1 is less than k sub 2, in that case we have to make sure that the parabola is in between them, right? And what can we do? Well, if we go with the x coordinate of the vertex, we can say the x coordinate of the vertex has to be greater than k sub 1 and it has to be less than k sub 2. So at least we can try that. So our second necessary condition is that the x coordinate of the vertex must be between k sub 1 and k sub 2. So let's make a quick note of that. Now, is the second condition sufficient to guarantee that k sub 1 and k sub 2 will not be inside the parabola? Actually, it is not. Because your k sub 1 could be inside the parabola and still be less than the x coordinate of the vertex. Similarly, k sub 2 could also be inside the parabola, however it could still be greater than the x coordinate of the vertex. So the second condition does not really guarantee that k sub 1 and k sub 2 will not be inside the parabola. It only guarantees that k sub 1 will be less than the x coordinate of the vertex and k sub 2 will be greater than the x coordinate of the vertex. So how are we going to guarantee that k sub 1 and k sub 2 will not be inside the parabola? Well, we are going to use our popular criteria, which is the product of leading coefficient and the value of the function at k sub 1 or k sub 2, right? So now let me show you what would be the value of the function at k sub 1 and k sub 2. So the two red dots on the function graph indicates the value of the function at k sub 1 and k sub 2, right? Now see, when the leading coefficient is positive, the parabola opens upwards. That means f of k sub 1 will be positive. Similarly, f of k sub 2 will also be positive. And now if we do the same thing on the diagram when the leading coefficient is negative, so let's take a look and see how that's going to look like. So here I have the diagram for quadratic equations where the leading coefficient is negative, and again here let me plot the k sub 1 and k sub 2. In the second diagram, I have plotted the 2 points k sub 1 and k sub 2 on the positive x-axis, and also I have indicated what would be the value of the function at k sub 1 and k sub 2, and that will be f of k sub 1, that would be the value of the function at k sub 1, and f of k sub 2 would be the value of the function at k sub 2. So now in this case, you see that both f of k sub 1 and f of k sub 2, they both are negative because they are actually below the x-axis, right? So they are negative values. So now if you think about it, when the leading coefficient is positive, the value of f of k sub 1 or f of k sub 2, they both are positive. And when the leading coefficient is negative, then f of k sub 1 or f of k sub 2, they both are negative. So now if you consider this condition that the product of the leading coefficient and the value of the function at that point, this product will always be positive regardless whether the leading coefficient is positive or negative. If this product is positive, then we can guarantee that the points k sub 1 and k sub 2 will be outside of the parabola. They cannot be inside the parabola, because if they go inside the parabola, then their sign will change. So to guarantee that the 2 points k sub 1 and k sub 2 are outside of the parabola, we have to use this condition, this magic condition, which is kind of like this. It is the leading coefficient time the value of the function at k sub 1, this has to be greater than 0, and similarly the leading coefficient times the value of the function at k sub 2, that also has to be greater than 0. That is when we can guarantee that k sub 1 and k sub 2 will be outside of the parabola. So let's make a note of that up there. So our third and fourth conditions are kind of like this. Leading coefficient times f of k sub 1 has to be positive, and leading coefficient times f of k sub 2 also has to be positive. And that is the complete set of conditions that we need to guarantee that the two roots of this quadratic equation will lie between k sub 1 and k sub 2. I hope everything made sense so far. Now we are going to take an example and see how we can solve problems using this concept. Suppose we have an example like this. We have a quadratic equation which is x squared plus p minus 5 times x minus 5 times p equals 0, and we have to find out the values of p for which the two roots of this quadratic equation alpha and beta will be between 1 and 6. So this is essentially our k sub 1 and this is our k sub 2. So we are saying that the two roots of this quadratic equation will be between k sub 1 and k sub 2, which is 1 and 6, positive 1 and positive 6. And we have to find out what are the values of p for which the two roots of this quadratic equation will lie between positive 1 and positive 6. So let's try to solve the problem. Since the quadratic equation is like this, we can say, well, then the quadratic function will be like this. We can say f of x will be equal to x squared plus p minus 5 times x minus 5 times p. That would be the quadratic function. Now what is our first condition? Well, the first condition is that the discriminant has to be greater than or equal to 0. So let's take the first condition. Now for this quadratic equation, what is the discriminant? Well, discriminant would be b squared minus 4ac. Now what is b for this equation? Well, b is actually p minus 5. So we can say that p minus 5 whole squared, that is b squared, minus 4 times, and a is 1, leading coefficient is 1 because x squared's coefficient is 1. So 4 times a times c. What is c in this case? Well, c is actually negative 5 times p, and this has to be greater than or equal to 0. That's one of the necessary conditions. So from here, let's try to solve for p. If we simplify it, this will be p squared minus 10 times p plus 25, and then we will have positive 20 times p, that will be greater than or equal to 0. And from here, can we write it like this? This will be p squared, negative 10 times p and positive 20 times p, that would be positive 10 times p. So that would be positive 10 times p, and then we have plus 25, that will be greater than or equal to 0. And then from here, what can we say? Well, this is actually p plus 5 whole squared. If you think about it, this is now p plus 5 whole squared. So we can write it as p plus 5 whole squared greater than or equal to 0. And from here, we can clearly see that p can be any real number. And even if you use the Wavy curve method, there also you will find that p can be any real number. Well, let's use the Wavy curve method quickly. What is the critical point for p plus 5? Well, critical point will be negative 5. Let's suppose that negative 5 is somewhere right here. Let's assume that is negative 5. On the right hand side of the critical point, the expression's value will always be positive. So I'm going to draw the Wavy curve like this. And how about on the left hand side of the critical point? Well, on the left hand side, whether the sign of the expression going to change or not, it depends on the multiplicity of this factor that gave us the critical point. Now in this case, you see the multiplicity is actually 2. That's an even number. And because the multiplicity of the factor is even, when you go to the left hand side of the critical point, then also the expression's value will remain positive. It will not become negative. It will remain positive. I have already created video on this concept. Feel free to watch those videos. I will provide the link in the description. So here we can see that no matter what number we pick from the real number line for p, we see that p plus 5 whole squared will be positive always, right? So p can be any real number essentially. So from here, here we can say, well, then therefore this one solution right here is that p can be any real number. So we can say p would belong to the set of all numbers from negative infinity to positive infinity. So that is our first solution. Now let's try to solve the second condition. Our second condition is actually two separate conditions. It's a combination of two conditions. What are those two conditions? Well, the x coordinate of the vertex, which is negative b over 2a, has to be greater than k sub 1, and also it has to be less than k sub 2. So those are the two conditions, right? And when we solve those two inequalities, we see that the value of p would be in the range of negative infinity to positive 3, and the second condition gives us the values of p from negative 7 through positive infinity. So far we have obtained three sets of solutions for the values of p, right? From the first condition we obtained one set of values, and then from the second condition we have obtained two sets of values. And then we are going to solve for the condition 3 and the condition 4, I mean the third condition and the fourth condition. So let's now try to solve the third condition and see how that looks. The third condition was kind of like this: a times f of k sub 1 has to be positive. Now what is k sub 1? Well, in our example k sub 1 is actually 1. So let me make a quick note here. K sub 1 is actually 1 and k sub 2 is actually 6. So let's try to solve this inequality here. What is a? For our example quadratic equation, the leading coefficient is 1. So we can say 1 times, what is f of k sub 1? Well, it is actually f of 1, because k sub 1 is actually 1 right here. So we can say this has to be positive. Now from here, what is f of 1? Well, f of 1 would be, I am replacing x by 1. So that would be 1 squared plus p minus 5 times 1 minus 5 times p, and all of this has to be greater than 0. And then from here, what do we get? Well, we get 1 plus p minus 5 and then minus 5 times p. This has to be greater than 0. And from here, what do we get? Well, if we simplify further, we'll have negative 4 times p and negative 4. This is greater than 0. Now if we divide both sides by negative 4, we will get positive p and a positive 1. The inequality sign will flip. That will be less than 0 divided by negative 4. That will be 0. So then from here we can say, well, looks like p has to be less than negative 1. So p is actually now less than negative 1. That means we can say, well, therefore we can say p will belong to the set of numbers between negative infinity and negative 1. So from here we can say that p would belong to the set of numbers between negative infinity and negative 1. So this is our fourth solution set for the values of p that we obtained so far. Now let's try to solve the fourth condition. The fourth condition is like this: the product of the leading coefficient and the function value at k sub 2, that product has to be positive. So let's try to solve it. So from here we can say, well, leading coefficient is 1 in our example. So we can say 1 times f of, what is k sub 2? Well, k sub 2 is actually 6. So 1 times f of 6 would be greater than 0. Now let's try to evaluate f of 6. Well, f of 6 would be 6 squared plus p minus 5 times 6 and minus 5 times p. That has to be greater than 0. And then if we simplify further, what are we going to get? We are going to get 36 plus 6 times p minus 30 minus 5 times p, and from here we have positive 6 times p and negative 5 times p, so that would be just a positive p, and then positive 36 and negative 30, so that would be positive 6. This is greater than 0, and from here we see that p has to be greater than negative 6. So we can say that p must belong to the set negative 6 to positive infinity, and that is the final solution set that we needed to find out. Now we have to take the intersection of all these solutions, because all our conditions are AND condition, in the sense that all conditions have to be true for the two roots of this quadratic equation to lie between positive 1 and positive 6. All conditions have to be true. That means we have to take an intersection of all these solution sets. So let's try to plot them on the real number line. Let me draw a real number line here. Our first solution set was that p can be any real number. So let's assume that this entire blue line here, this is our real number line, and let's assume that this entire blue line is the solution set from the first condition. And then what was the solution set from the second condition? From the second condition, the solution set was that p should be in the range of negative infinity through positive 3. So from negative infinity to positive 3, that will be this zone right here. I am using a dotted pink line to show that zone, which is from negative infinity to positive 3, both excluded of course, because all these conditions are strictly less than or greater than condition. So none of those numbers would be included here. And then the next solution that we obtained was p must belong to the range between negative 7 through positive infinity. So between negative 7 through positive infinity, what would be that range? So let me indicate right here. So obviously negative 7 excluded. So then it will be a range like this. I'm using the green color to indicate that. And then our two other solution sets are p must belong to the range of numbers between negative infinity and negative 1. I'm going to use a yellow color now. So from negative 1 to negative infinity, it would be a range like this. And the last solution set, which says p must belong to the range between negative 6 through positive infinity. So let's plot that also. And for this one, I'm going to use the red color. And now we have to take an intersection. Now intersection means the common zone where all these ranges coincide. So what would be that common zone? Well, if you think about it, we have how many zones here? We have the entire real number line, that is one solution set. Then negative infinity to negative 1, that is one solution set. Then negative 6 to positive infinity, that is another one. Then negative 7 to positive infinity, that is another one. And then positive 3 to negative infinity, that is another one, right? Now if you carefully look at it, you will see that the common zone for all these 5 solution sets would be kind of like this. Let me kind of highlight that zone right here. I'm going to highlight that with a green color on the real number line itself. So the common zone would be right here. This would be the common zone. If you think about it, that this one particular zone from which if you take any number, that would satisfy all these 5 sets of solution. So finally we can see that p must be between negative 6 and negative 1 for this quadratic equation to have both of its roots to lie between positive 1 and positive 6. So let me write down the final solution here. So p must belong to the range of numbers between negative 6 and negative 1. I hope everything made sense. Thank you for watching. See you in the next video.